Good afternoon, everyone. We're going to go ahead and start talking about chemical equilibrium, and I'm adjusting a PowerPoint that I've used from another textbook. I tried to make some adjustments, but we're going to do a little bit with this in class that I think should help maybe to make a little bit more sense. Let's go ahead and jump into it. Now, the overall goal is, of course, at level 3, that you'll be able to apply basic principles of chemical equilibrium to chemical reactions and show how it applies to kinetics or reaction rates. As we talked about in the last video, there are certain things that we can sort of do to manipulate and deal with the reaction. One of the things that we've realized is that not all reactions go just in one direction. We actually can have something that reaches a point of equilibrium. Let's go ahead and discuss what that means. Now, equilibrium is the state where concentrations of all reactants and products remain constant with time. Well, let's look at the example given. So we have dinitrogen tetroxide. Normally we would look at it as though it only goes in one direction. It breaks down and it becomes our two molecules of nitrogen dioxide. But this process is going to happen over and over, and it's going to continue to change. So we note this by just drawing a double-sided arrow. This lets us know that the reaction can go in both directions depending on the temperature and so forth. I included a short video here, and it just shows how as we manipulate the temperature of many of these substances, we can also manipulate the reaction and force it to go one way over another. As it cools down, it clears up, whereas before it actually remained very, very dark. Now, let's see what this looks like in terms of our reaction. If I'm looking at something that is, at equilibrium, most times for all intents and purposes, it seems like nothing's happening anymore. It seems like our overall process is kind of stopped, which doesn't really look all that exciting. But if we were able to zoom in down to the microscopic level, we see that it's constantly changing. We have this shifting back and forth. We have products that are being formed, and at the same time we have some of our products that are breaking down and going back towards the reactants. And so we say that it's macroscopically static or stagnant or not moving, but microscopically it's changing and it's developing and it's constantly moving. Now, here's another reaction that's given to us. As we look at how the concentration changes, note that our hydrogen we're decreasing, our nitrogen we're decreasing, and at the same time we're forming our ammonia. At the point where we hit equilibrium, note that they're not at the same value for concentration. They are not at the same value for concentration, but they've each sort of leveled out. This is that point that we know we've hit equilibrium. They're still going to be changing, they're still going to be adapting, but the concentration changes don't vary much from where they originally started. Now, let's look at it in terms of the rate. Now, the forward rate, or the breaking down of our nitrogen molecules and our hydrogen molecules, is going to decrease greatly. And the reverse rate, which is breaking down the ammonia itself back into those products, they're both going to continue to change. But when we hit equilibrium, what's going to happen is the forward rate is going to be equal to that of the reverse rate. So again, note, the concentrations aren't equal. That's not what we're doing there. But the rate at which they're forming and breaking down becomes even, or becomes constant over a period of time. That's how we know when we've hit equilibrium. Now, we're going to move into part 2, which is going to look at how shifting or how changing certain things will allow us to be able to manipulate that reaction. One of the first things we need to look at, though, is writing what we call our equilibrium constant. Now, because of the fact that we are looking at a reaction, we want to do a ratio that's going to let us know which side of the reaction is favored or most likely to happen. And so we call this capital K, or the equilibrium constant. We write this based on the equation that we see above, in this way. It's always going to be our products. So notice that these were our products over the reactants. I'll just put P over R. So each of these, C and D, would be our products. And notice that the coefficient that was here becomes the exponent. Okay. Now, are we going to have to do a whole lot of calculations with these? Not this year. But we want to understand how it sort of works. Okay. So when we give that value of K, that ratio of products over reactants, this is going to let us know which side of the reaction is favored. And you can't see me, but I'm using air quotes. What do I mean favored? Well, although we are eventually going to hit that point where the forward rate and the reverse rate are equal to each other, or a constant over a period of time, one side might be a little bit bigger than the other. Because of that, we say that that side of the reaction is favored. So we start dealing with things whether they're reactant favored, meaning the reaction really doesn't happen without a lot of input, or they're product favored. With very little input, we're going to produce a lot of this material. The further away from these values we are, the more we can say the side is favored. Now, this is usually going to be expressed without a unit. So we just say K equals whatever. We don't have to worry about moles or grams or anything at the end of that one. Now, if I have a set temperature, so if I say this is happening at 450 degrees Kelvin, the K value will not change as long as the temperature is the same. So I can change up the concentration, the amount of moles, all those things, and they still have no effect. But if I change the temperature, my K value is all messed up. Everything changes up for me, okay? So you want to make sure that you keep that in mind and we don't end up with issues of, well, they changed this or they changed that. Now, this is how we understand what's going on with K. Everything is relative to 1. So 1 is sort of our golden number. The larger values, if it's greater than 1, it means that the product concentrations or amounts are so much greater than those of the reactant. We say that the reaction then goes to completion, or it is product favored, or equilibrium lies to the right. These are 3 different ways of saying the same thing. But if we have something that is less than 1, the smaller the value is, that means the larger value is on the bottom and the smaller value is on the top, we say that it lies to the left, or on the reactant side, or it's reactant favored. This may mean that I have to put in a lot of energy in order to reach the activation energy point for the reaction to continue. This is usually going to be an endothermic process, whereas if I have something that is going to be greater than 1, it might be very, very exothermic. This is where we'll have to get into things like whether something is spontaneous or non-spontaneous. No, spontaneous doesn't mean spur of the moment. Let's go and do this. Let's make things explode. Although I do enjoy that. But spontaneous versus non-spontaneous is telling me whether or not I have to keep putting in energy for the reaction to proceed, or if it goes on its own. We're going to talk more about this, of course, in class. We're going to do some practice with it. We're going to answer some questions and all these things to sort of get you the full picture of what's going on. This is where we're going to go ahead and end this video. I appreciate your time. Make sure you take your notes and write down any questions that you have so that we can address them in class. Have a great day, and I'll see you tomorrow.